Time. What is it? Where does it begin, and where does it end? Was there time before the Big Bang? Or will time eventually come to an end? When our solar system reaches its limit, or when we no longer exist, will time still exist? Is it an independent, unbroken line, moving forward regardless of everything? According to early physicists like Galileo and Newton, yes, time is absolute, unchanging, and flows independently. When we think of absolute time, Newton usually comes to mind. But there was a young man working in a patent office in Bern. Do you remember him? One day, he wrote in his journal, "Newton, I'm so sorry." With this statement, he was, in a way, challenging legends like Newton, Descartes, Galileo, and Maxwell, people who transformed the course of history. He was saying, "Gentlemen, I'm sorry, but things aren't quite what you thought." This rebellious young man was Albert Einstein. As a student, he once said, "I'm not concerned with this phenomenon or that phenomenon. I want to know God's thoughts. The rest are details." Even an hour before his death, Einstein was holding his notebook and pen, attempting to complete the theory of everything, the final piece to understanding the mind of God. We will talk a lot about Einstein, his triumphs, his mistakes, his entire perspective. But today, we're here to discuss time. To understand and explain time, we first need to go back to the very beginning. Don't worry, we won't delve into Greek mythology or ancient philosophers. This is a topic Aristotle and Copernicus also pondered. We could discuss them separately, but our focus will be on when time was scientifically studied for the first time. Let's travel back to the 16th century. What a century! Galileo, Newton, Barrow, Descartes. A true age of enlightenment spanning into the 17th century. It all began with Galileo Galilei studying time, and Isaac Barrow and Isaac Newton, who gave us the concept of time that would be accepted for centuries. To all of these scientists, time was absolute and universal, as we mentioned earlier. This kind of time, defined as Newtonian time, was the same for everyone, advancing at a constant speed, present throughout the universe, a measurable, yet intangible entity. Newton particularly believed that time and space were entirely separate aspects of objective reality. He thought that even if nothing existed in the universe, time would continue independently. Shakespeare once wrote, "All the world's a stage," and to Newton, time was the one thing on this stage that never changed. In explaining the laws of motion and gravity, Newton treated time as constant and untouched. This is why we mentioned there was a problem Newton couldn't solve in his lifetime. He thought it might be a divine matter, something beyond human perception. The clearest sign of this problem lay in the orbit of Mercury. Newton's laws could predict everything, from the motion of an apple to Earth's orbit, but Mercury refused to follow these calculations. Its orbit showed a deviation. When some scientists tried to explain this, they hypothesized the existence of an unseen planet, Vulcan, to account for the gravitational influence. However, it wasn't there. The discrepancy in Mercury's orbit defied all known laws, and as long as time was considered constant, there was no solution. Here, I ask you something challenging. Try to forget everything you think you know about time, that it passes as a straight line, that we experience life as a journey from birth to death, that time is the same for everyone, regardless of where or how they live. Forget all of it, because this perception needs to be broken down. It's wrong. All of it is wrong. Who said this first? Wilhelm Leibniz. According to Leibniz, only events that happen before, after, or at the same time exist. And time is just our mind's way of organizing these relations. Later, Immanuel Kant, approaching it from a philosophical perspective, argued that time didn't exist independently or as a sequence of relationships between independently existing things. According to Kant, time was simply the way our minds organize experiences. Kant argued that things existing independently of us and our minds were in fact not within time itself. Yet Albert Einstein would ultimately settle this debate. In 1905, known as Einstein's Miracle Year, he published 4 groundbreaking papers, including the theory of special relativity, and then over a decade later, he unveiled his general theory of relativity, securing his place in history. These are not concepts that can be explained in a single sentence. We'll dive into the details later, but let's stay on track. We were talking about time, so what is time? For Einstein, a Newton enthusiast, this question was deeply troubling. After studying Maxwell's equations, Einstein became certain of one thing. The only true constant in the universe was the speed of light. No matter where you stood or how you looked at it, the speed of light remained the same, unchanging. This meant that something had to change in Newton's laws. Some things couldn't remain constant, especially time. Let's examine this with a hypothetical scenario, the sun disappearing in an instant. If we approach the scenario with Newton's law of gravitation, here's what would happen. The Earth would immediately veer off its orbit and head into the void. According to Newton's law, 2 objects that exert gravitational pull on each other are connected as if by a rope, with an instantaneous force pulling them together. But Einstein declared this impossible, since the only true constant in the universe is the speed of light, which nothing can exceed. This speed is our universal limit, and it takes sunlight about 8 minutes to reach Earth. Since gravitational force also travels at the speed of light, if the sun were to disappear now, we would continue orbiting as usual for 8 minutes, unaware that anything had changed. This discovery became one of the most important in the history of science. Strangely though, we could have continued on, relying on Newton's laws, and might never have realized it. In our everyday experience, this isn't something we notice. Newton could calculate the movements of the objects in the solar system with 99% accuracy. But that remaining 1%? That mattered to Einstein and people like him. For them, everything had to have an explanation. How did Einstein come to this conclusion? He actually realized this at age 16. Einstein was famous for his thought experiments, which he used to visualize situations and explore them mentally. In one thought experiment, he imagined 2 people, one on a speeding train and one observing the train from outside. Along the track, 100 meters apart, 2 trees stood, and lightning struck both trees at the same time. For the observer outside, this happened simultaneously, but for the person on the moving train, the lightning would hit one tree first, then the other. Same event, 2 people, 2 different times. How could this be? Now let's try to illustrate the constancy of the speed of light with a slightly different example. In everyday life, speed is relative and calculated based on reference points using addition and subtraction. Imagine 2 cars traveling side by side, each going 60 kilometers per hour. For the people in each car, the other car's speed, relative to their own, is 0, meaning it appears stationary. But if one car speeds up to 80 kilometers per hour, it would appear to be moving at 20 kilometers per hour relative to the other car, moving at 60 kilometers per hour. This is the basic rule, but this logic doesn't apply to the speed of light. The speed of light is exactly 299,792,458 meters per second. For simplicity, let's round it to 300 million meters per second and imagine a spaceship moving at 150 million meters per second. Normally, if we were to measure the speed of a light particle from this spaceship, wouldn't we expect to see a result of 150 million meters per second? But that's not what happens. No matter where or how you measure it, the speed of light will always be exactly 299,792,458 meters per second. This is where Einstein's famous equation E equals mc comes in. You've probably heard of it. Here, E stands for energy, m for mass, and c for the square of the speed of light. When Einstein first wrote this equation, he wrote it as mem equals EC, meaning that energy and mass are interchangeable. Brace yourself, because they are actually the same thing. Everything you see, touch, or observe is, in fact, energy. Let's take a paperclip. If we could convert every atom in that paperclip into energy, it would release the equivalent of 18 kilotons of TNT, close to the force of the bomb dropped on Hiroshima. Einstein's equation then tells us this: as an object's speed increases, its energy and mass increase too. To reach the speed of light, it would need infinite energy and therefore infinite mass. This is why surpassing the speed of light is impossible. The main point that challenges our perception is this: according to our understanding of physics, speed multiplied by time equals distance. But when you put the speed of light into this equation, the usual rules of physics as we know them don't apply. As I mentioned, the speed of light is constant. Therefore, time and distance must adapt accordingly. Let's wrap up with one final example. Imagine twin siblings named Alice and Bob. Both are astronauts, and they participate in an experiment to help us understand this law. Bob stays on Earth, while Alice embarks on a one-year journey in a spaceship capable of reaching 99.997% of the speed of light. When this journey begins, let's assume they are both 30 years old. After 1 year, when Bob and Alice reunite, Alice will naturally be 31. But Bob, who stayed on Earth, will be 81 years old. For someone moving at that speed, time would slow down significantly, meaning Bob and Alice would become the first twins with a 51-year age gap. This theory, by the way, was proven in real life in 1971 in what's known as the Keing experiment. 3 synchronized atomic clocks were used. 2 were placed on planes, flying in opposite directions, one eastward and the other westward, while the third stayed at the airport. When the planes landed, the clocks were no longer synchronized. The clock on the eastbound flight was behind by 59 billionths of a second, compared to the one at the airport, and the westbound clock was behind by 273 billionths. Hard to believe, isn't it? It's almost impossible for our minds to accept. But even just one example affecting our daily lives might be enough to show us the importance of this theory. Take GPS systems, for example. Satellites in orbit move at extremely high speeds, creating very slight time differences, and these differences are constantly synchronized. Otherwise, when you check your location on Google Maps, it could be off by kilometers, and it would be impossible to pinpoint anything accurately. All of this is a very brief summary of the theory of special relativity, which Albert Einstein published in 1905. I haven't even touched on gravity, general relativity, or the quantum world where Einstein himself faced challenges. So we're really just getting started. All these laws, theories, and examples. At some point, we might ask ourselves, what does this mean for my everyday life? I sometimes wonder that myself. It's so difficult to grasp, almost to the point of wanting to give up. But then, I find myself thinking about the universe and the energy I mentioned earlier, about how all of us and everything are made of energy, about how time is completely an illusion, and how everything, our perspectives on events, problems, concerns, joys, sorrows, how everything is relative depending on where we stand. When I think about all this, I feel that physics is telling me about myself. It changes my perspective entirely on life, the universe, social issues, politics, matter, psychology, and on myself. That's why I say let's see what we'll learn about ourselves in the next video. Shall we meet again at the first opportunity? Until then, take care of yourselves. And as always, thank you for being here. Best wishes. Don't forget to like, share, and subscribe for more content like this. And remember, you are valuable.